the CCENT journey with me, Ryan. In this next section, we're going to have a final look at the overall switching process and a review of how ARP actually works. We have a lab set up and we're going to go through the processes that are involved in getting connectivity on a local segment. For those who don't know, you can contact me here on YouTube, on LinkedIn or Twitter. So we're just going to bring up a slide that we talked about in the last video, but you can see that I've modified it a little bit because at the bottom I've actually put together the topology that we will actually be using. We have PC1 and we have PC2. PC1 is configured with 192.168.0.1 and PC2 has been configured with 192.168.0.2. PC2 connects into a layer 2 switch on port 23 and PC1 connects on port 19. The switch in the middle currently has these interfaces here in the shutdown state, meaning essentially they're turned off, and we're going to enable these interfaces and we're going to look at the chatter that happens on the line and the ARP resolution between the two devices, allowing them to communicate with a destination IP that is on the subnet. We said that what we would expect to find is PC1 will try to send data to PC2, but unfortunately we'll be missing the destination MAC address to put into its layer 2 frame, and because of that the ARP process will kick in. A ARP request will be sent from PC1 asking for the device with 192.168.0.2 to respond with an ARP reply with the MAC address of its device, which will then in turn enable PC1 to create the frame and send the traffic towards the correct host on the network. So what we're going to do now is jump into the lab that I've got set up and we'll have a look at this process in real time. Okay, so here we are inside the environment. We have PC1, a switch, and PC2. One thing to note, first of all, is PC1 and PC2 aren't actually PCs. Like, they're not Windows, they're not Linux, they're actually Cisco devices. There's other switches, but I've actually turned them into layer 3 ports, and essentially they're going to perform the ARP process just like any other device would. So even though they are switches, for this demonstration around ARP and the switching process, focusing primarily on the switch in the middle, whether the end clients, PC1 and PC2, whether they're Linux, Macs, other switches, other routers, the ARP process is the same throughout. Now, like I said in the previous slide, the switch has actually got both its ports in the shutdown state connecting towards PC2 and PC1. So let's go ahead and confirm that. You can see that both of them here, 19 to PC1 and 23 to PC2, are currently shut down. Now if we were to, let's say, bring one of them up, in this case let's bring the port towards PC1 up, we're going to simply say no shut to bring it back into life. When we do that, we're going to get an output telling us that the state went from down to up. And then if we go over to PC1, we have the same state. It's gone from down to up. Now, what we can do at this point is we can actually perform a debug. And a debug is a type of command that will give more in-depth of an understanding of what's happening behind the scenes rather than just a show output. And in this case, what we can use is the debug ARP. Okay, so now we've got that debug on, what we're going to do is attempt to send some traffic towards PC2. But let's have a think of what would actually happen here. Well, if we go back to our diagram, we have a PC. That PC connects directly into a switch, which connects into another PC. And like I said, those PCs are actually switches, but the concept still applies. Now, if you remember, I said that the switches, or the switch ports here and here, were in the shutdown state, whereas at the moment the only one that's shut down is the link towards PC2, where the link towards PC1 is currently up. Now because of that, the interface is up and PC1 believes that it's able to communicate with the rest of the network. Now obviously there's no one out there to communicate currently, but if we were to attempt to send traffic, it would try its ultimate best to get out there and communicate with the destination. So in this instance, what we're going to do is try to communicate with PC2. And we're going to do that by initiating a ping towards 192.168.0.2, and we're going to repeat it once. Now PC1 will then look at the interfaces that it has configured, and it will notice that gig 0/19 has been configured with the 192.168.0.0/24, and inside that range the .1, so 192.168.0.1/24 lives on gig 019. And because I'm trying to communicate with an IP inside that /24 range, it knows which interface to send the traffic out. In this case, which interface to try and send the ping request. Okay, so you can see here that we've tried to ping the 192.168.0.2, and rightly so, it's failed because this link here is currently in the shutdown state. But what it has done is it showed us the process that PC1 is trying to actually achieve, and you can see here it's created an incomplete ARP entry. It knew it tried to communicate with 192.168.0.2 because that was the information we gave it. It then done a recursive lookup and found out that the 192.168.0.0/24 is reachable out of gig 019, and it tried to populate the ARP information. It knew everything apart from one very important bit. It knew the source IP because we've configured it on that interface. It knew its source MAC address because on this interface obviously it has a NIC card, and that NIC card has a MAC address, and it knows its local MAC address. It knew the destination because we gave it the destination, but it didn't know the destination MAC address, and because of that it had to evoke this ARP request to try and ask whoever is 192.168.0.2, please respond to me. All this ARP information is then packaged up and put into a ARP packet, which is then attached to an Ethernet header and sent onto the wire. Now inside that Ethernet header, it's going to have the source of the PC itself. So inside here it's going to have the source of, it was 001B D5 75 C5 C2, and the destination, any ideas? Well, it can't be all 0 because all this ARP information down here, remember, is inside the payload of the ARP request. Well, the destination here is all F's. So when this information is received by the switch looks at the Ethernet header, sees the destination of all F, and knows to flood it to everyone. Every host connected to the switch who receives this frame will have to process it because it's to the destination of all F's. It's a broadcast. They will all decapsulate the Ethernet header, look inside, realize it's a ARP request, and look at the ARP destination, and if it's the IP address of the local PC, that PC will respond with an ARP reply. In this case, PC2 would respond. If there was PC3 and PC3 received it, he would receive this ARP because it's going to the all Fs. He would decapsulate the Ethernet header, look at the ARP request and say, hey, I'm not 192.168.0.2, therefore I will discard that traffic. And going back to our slides, here's an example of an ARP request. We can see at the top, we have this bit here that says frame. This is read as what's in the entire frame. So what's actually going to go onto the wire as ones and zeros. We can see we have this section here, which is the Ethernet. And then we can see we have this section here, which is the address resolution protocol, which is an actual request, which is this part. And you can see inside the request, we have the sender MAC address, the target MAC address. And as I said, we don't know the target MAC address. That's what we're trying to actually achieve. But we know our IP address, and we know the target or destination IP because we typed it in on the command line, because that's what we're trying to reach when we do our pings. We know all the information apart from this target MAC address. And at the top we have the Ethernet header itself that shows the all-Fs address, which is a broadcast, and the source, which mirrors what's actually inside the ARP packet. Now obviously if you look at the MAC addresses, particularly the source MAC, it doesn't mirror up with the device that we are currently working with. That's because these were simply downloaded from the internet. Links will be in the description. But what's key to understand here is there's an Ethernet header on top of the ARP. So a lot of people will get confused here because they get confused between the target MAC address and the destination address. Remember that these are two different parts. So now we know what the structure looks like and we know what PC1 is trying to do to communicate with PC2. Let's look into the switch and have a look at what the switch has learned because of this ARP request. Okay, so we're back in the switch. Now we said in the previous video that switches learn based on the source and switch or forwards traffic based on the destination. Now the ARP request would come in from PC1, and the ARP request will have a source of its MAC address and the destination of all Fs. If we look at the show MAC address table, and we're going to put a switch on the end of dynamic, and this is asking the switch, hey switch, can you show me all of the MAC addresses that you've dynamically learned since connected to the network. And again, like I said, there is an aging process that happens on the MAC address table to ensure that it's kept up to date. And we can see, rightly so, that there's a MAC address that's been learnt. It was learnt out of port gig 019, which we know goes off to PC1. We can see that it was dynamically learnt, meaning nobody statically configured it, nor is it a MAC address that's listening for what we call control plane traffic. This would be things like the spanning tree protocol, the VLAN trunking protocol, CDP, and so forth, all of which we'll get into later. And you can see the MAC address that I actually learned on that port. If any traffic came in on port gig 019, let's say PC1 attempts to send another ARP request into the network, that will refresh the timer that's associated with this MAC entry, because obviously the MAC entry is now already learned. But what we do know now is because this switch knows that that MAC address is reachable outside port 019, that if PC2 were to reply, PC2 will actually put in its headers none of the broadcast traffic, but actually the specific information for PC1, and when the switch receives it, the switch will know that the MAC address of PC1 lives out of a port, and therefore the switch wouldn't need to broadcast it. But we'll get onto that in a moment when we see what switch or what PC2 actually responds with when we enable the port towards PC2. So while we're here then, we're going to enable the port towards PC2, which is port 23, and in order to do that we need to go into the global configuration, into port 23, and the previous command was shutdown to shut down the interfaces. We now want to know that interface, effectively turning on gig 023. Doing this will bring up the message to say that the interface has gone from down to up, and if we go across to PC2 we'd see the same message on here. Now going back to PC1, you can see it's timed me out. What we're going to do is we're going to try pinging PC2 once more. If we do show debug, we can see that the ARP packet debugging is on. So let's go ahead and ping 192.168.02 with the repeat of 1. And the repeat of 1 means only attempt to send one ICMP packet. And it's a success. We can see that a ARP entry was completed. We can see again, just like before, it was sent for the 192.168.02. It was recursed and sent out the right interface. We can see the source of PC1, the destination of PC2. Again, we had all those zeros because we didn't know PC2's MAC address. We did know our own MAC address, and it was sent out of this interface. And you can see that we received a ARP, which is obviously short for a reply. The reply was from 2, and they gave us their MAC address. And you can see that that reply was sent back to me on 192.168.02, and it was received inbound on my ingress interface, gig 019. Here is the ARP reply that would come back. First of all, we can notice that the destination is not the all Fs, and the reason for that is because the receiving host knows who sent the original ARP request, and it doesn't need to go to everyone, so it goes back to the source MAC address of the ARP request. And again, there's our Ethernet frame, and PC2 would put its MAC address as the source. And you notice down here inside the ARP reply, you would notice that we have now all the fields correctly filled out. And because of this, both PCs now have the IP to MAC resolution for both PC1 and PC2, and a knock-on effect of that is the switch in the middle also has learned from both the broadcast and the unicast traffic between the two devices where PC1 and PC2 actually live within all of its switch ports. And because of that, unicast communication can happen between those two hosts, and PC1 and PC2 will now be able to successfully build their layer 2 frames towards one another. Okay, so going back to the switch, press the up arrow to repeat a previous command and look at the MAC address table. We now can see that both PC1 and PC2 has been learnt by the switch. This means any communication between these two devices, the switch will know how to reach them. And also, with the ARP now completed on the actual end host, we can ask what the ARP cache looks like. So you can see if I do show IP ARP, you can see if PC1 now needs to communicate with PC2, PC2 has a ARP entry for it with this MAC address, and it knows it's reachable out this interface. So PC1 knows how to build the frame, and switch 2 will know what interface to unicast forward the frame. Now, one other thing to keep in mind here is what's called an unknown unicast. Now this is where PC1 knows where to send the frame because it has the ARP entries inside its cache, but the switch doesn't have any information. So for example, now I've cleared the MAC addresses inside the switch. The PCs still have their ARP cache locally, so they still know how to communicate with one another. But when that frame comes into the switch doesn't know where those MAC addresses live. So the switch will have to flood that traffic out initially, and when it's flooded out, it's referred to as an unknown unicast because the end host is trying to do some kind of unicast communication to one another, but the device in the middle is unaware of how to reach the destination layer 2 MAC address. Okay, so that's all we've got time for in this lesson. This was the third video regarding the switching and ARP process. Teaching those technologies together tends to help cement both of them because switching is a bit of an odd thing to learn, same with ARP, but when you put them together they kind of make a lot of sense because ARP is a good example of how the switching process actually works, and of course the switching process then shows you how and why ARP is needed. We reviewed the ARP cache that's inside each host, and then we looked at the MAC address table. We looked at those dynamic entries and how the ARP cache is built, the MAC address table is built, and then we cleared the MAC address table and talked very briefly about unknown unicast. Very importantly, we looked at some packet captures. We had a packet capture of an ARP request and an ARP reply. We looked at the different fields inside that packet capture. The packet capture will be linked below. You would have to get a free application called Wireshark to actually view those packet captures, and that will give you an idea of what the actual frame looks like when it's sent onto the wire. I hope this video has been informative. I'd like to thank you for viewing, and if it has been, please do like and subscribe.